Welcome back, friends, to this optical fiber session. So today we are going to have the second lecture. So to begin with, here many more the important the parameters associated with the optical fibers we are dealing. The first one is fractional index change, which is denoted by delta. So it is defined as it is the ratio of the difference between the refractive indices of core and cladding to the refractive index of core. That is delta is equal to n1 minus n2 divided by n1. The difference in the core and cladding refractive index, that is n1 minus n2 divided by n1. And the value of this, the delta is of the order of 0.01. Somewhere it's very less. So what we will come to know from this is the refractive indices of core and cladding, that is n1 and n2. They are very close to each other. And this order is of the order of, as I said, 0.01. It means if there is a large difference between core and cladding, refractive index of the core and cladding, so it leads to some distortion, some that is called as the dispersion, that we are going to discuss in future. So to avoid all those the distortion, so better the difference between n1 and n2 is minimized as much as possible. Next one, the very important aspect about the optical fiber is numerical aperture. So whenever we want to get the optical fiber from the market, specifically we have to mention the numerical aperture of the optical fiber. So this numerical aperture, it plays a very vital role in the optical fiber. What that exactly the numerical aperture is? So in general words, okay, we can say it is the light gathering capacity of an optical fiber. Means how much amount of the light can get into the core of the fiber, that we are going to call it as numerical aperture. But mathematically or systematically, if you want to define it, when we can define it as, it is the sign of an acceptance angle is known as numerical aperture. That is the sign of the acceptance angle. Here numerical aperture is nothing but sine of theta a. So this and therefore numerical aperture is equal to square root of n1 square minus n2 square, because sine theta a, that is for the acceptance angle, we have, while that derivation we have proved that sine theta is equal to square root of n1 square minus n2 square. Therefore the expression for the numerical aperture is square root of n1 square minus n2 square. So it clearly once again shows that it only depends upon the refractive indices of core and cladding. Next, we want to establish the relation between the fractional index change delta and the numerical aperture. Since we know that numerical aperture is given by square root of n1 square minus n2 square, so this n1 square minus n2 square may be written as n1 minus n2 into n1 plus n2. It may be rewritten. Next, the next step is, since n1 minus n2, here this n1 minus n2, that is from the del, we know that n1 minus n2 is del into n1, so that we have substituted here, and n1 plus n2 as it is. And as we discussed previously, the value of n1 and n2, they are very close to each other. Therefore we approximate n1 is almost equal to n2. So with this approximation, Later on the numerical aperture is equal to square root of n1 as it is and delta also as it is. This n1 plus n2, as n1 is equal to n2, it may be written as 2n1. Then rearranging the terms, we get numerical aperture is equal to n1 into square root of 2 into delta. So this is the relation between the numerical aperture and the fractional index change. And the value of the numerical aperture, it lies between 0.13 to 0.50. So this value varies from single mode to multi-mode, those which we are dealing in the next session. So the numerical value exactly lies between 0.13 to 0.50. It varies between these two values. Now with this, the fractional index change and the numerical aperture. Now we'll get into the different types of the optical fibers, how the optical fibers are broadly classified. So the general classification we are going to see here. The optical fibers are mainly classified on two factors. One is based on the refractive index and second one is based on the mode theory. Now once again, on the basis of the refractive index, there are two types are there. One is the step index and second one is the graded index. Similarly, in the mode, there are two types are there. One is single mode and second one is the multi-mode. So what exactly is this? The refractive index, the mode concept, step index, graded index, single mode, multi-mode, everything we will discuss in detail. So before that, we will try to understand what exactly the refractive index profile is. So this refractive index profile, it may be defined as a refractive index profile for an fiber. It is a plot of refractive index on horizontal axis versus the distance from the core axis drawn on the vertical axis. So along the horizontal axis, the refractive index will be there, and along the vertical axis, the distance from the core from the axis is taken into account. So this is known as the refractive index profile. This will come to know with the particular diagram, we will come to know what exactly the refractive index profile is. Next, the second one is the mode concept. What exactly the mode concept is? So mode, it refers to the number of the paths the light ray that can travel in a given fiber. It means how many number of the ray of the path that they are going to, the various paths, the paths that are going to travel through the fiber, we are going to call it as the mode. So with this, once again the mode concept with the diagram, the ray diagram, it is easy to understand both the refractive index profile as well as the mode concept. Now, before getting into the classification of the optical fiber, so one more the parameter is associated, that is known as the V parameter, or sometimes it is known as normalized frequency. So the normalized frequency V, it is a dimensional parameter. So this will help us to find out how many number of the modes a fiber can have, or a fiber can sustain. So to calculate that one, first we have to find out the V parameter or the normalized frequency. So this is given by an equation. V is equal to 2 pi by lambda a into square root of n1 square minus n2 square. This n1 square minus n2 square is nothing but, already we are aware, it is nothing but the numerical aperture. Even in case of square root of n1 square minus n2 square, we can write any numerical aperture. It is also acceptable. So in this equation, lambda is the operating wavelength, means the wavelength which is passing through the fiber. A is the core radius of the fiber. N1 and N2 are the core and cladding refractive indices respectively, or even if you know the numerical aperture, directly you can put it there. Now with this, the V parameter, the number of the modes the fiber can have is given by the formula n is equal to V square by 2. So this n, it gives the number of the modes the fiber can have in a while it is propagating in a given fiber. Hence V parameter actually determines the number of the modes the optical fiber which is going to support. Now based on this, the V parameter, so this, the value of the V, if it is less than or equal to 2.405, we are going to call it a single mode, and if it is more than, V is more than 2.405, we call it as multimode. So this, the single mode and the what the exactly the multimode, we are going to discuss in the next slide. So as we have discussed, based on the refractive index, there are two types. One is the single mode and the based on the mode concept, there are two types are there. One is the single mode and the multi-mode. First we will try to understand what exactly the single mode is there. So this is the core of the fiber, and surrounding the region is the cladding, the cross-sectional view what you have taken. If you take the optical fiber, at the center we can see this is the core of the fiber and this is the axis of the fiber. Similarly, the cladding will be there surrounding the core. Here the important thing is that single mode means only one mode. Only the fundamental ray of mode can be transmitted to the fiber. It means only one ray of path it is possible to have in the given optical fiber. That's why it is known as single mode. Only one mode exists. So this is a single mode fiber it has a very thin core, okay, in which it allows only the one ray of path to propagate down the fiber, and the design is such a way that it allows only the fundamental mode to propagate down the fiber. Only the fundamental mode for that particular wavelength will be propagated inside the fiber. And as we discussed in the previous case, based on the V parameter, the value of V is less than or equal to 2.405. So this is nothing but the single mode, means only one mode, only one ray of path can travel inside the fiber. Next, similarly we are going to discuss about the multi-mode. First we will try to discuss the diagram. In the multi-mode, the core of the fiber is larger compared to the above one, and similarly the cladding is also very large. And coming to the ray path, we observe that different colors here. So the different, it means a ray of light can have different paths. So many more number of the ray of path it can have, more than one the ray of path can travel inside the optical fiber. So this is nothing but the multi-mode. Clearly it is visible, the different colors we can see. It means that particular multi-mode, it can sustain more than one ray of path. That's why it is called as multi-mode, more than one mode. That's why we call it as multi-mode. The same we can define here. A multi-mode fiber has a core of a larger diameter, which is larger compared to the wavelength of the light which is being transmitted, whatever the wavelength we are transmitting. So compared to that one, the dimension is larger, and usually, as we discussed in the previous slide, the value of the V is greater than 2.405, and it can transmit a large number of guided modes, means more number of the modes can be transmitted. So due to this, the large core size and a higher numerical aperture, it is very easy to launch the light inside the optical fiber. Even the ordinary the sunlight, whatever the outside, whatever the light is there, so that if a end of the fiber is hold to that, easily from the other side we can see that light is propagating. But this is not the case with the single mode fiber. So in the single mode fiber, it is very difficult to launch the light because the core is very thin here. So it is very difficult to launch the light inside the optical fiber, whereas in the multimode, easily we can launch the light into the fiber. So based on the refractive index profile, so as we discussed, there are two types are there. One is step index and the graded index. Now what exactly the step index? So in the step index, usually once again this is the core and the cladding of the fiber. Here this is the right hand side, this is the refractive index profile, we generally call it as. So this dotted line, it corresponds to the core dimension, and this corresponds to the cladding dimension. Now what we observe is, so there is the step index, means there is a step change in the refractive index as we move from core to cladding or cladding to more. So this we can show it here. So from the cladding, as we move towards the core clad interface here, this is the core clad interface. So we observe that from cladding, as we move to the core, there is a step change. There is a step change in the refractive index. Similarly, as we move from core to cladding here also, so there is a step change in the refractive index. Once we move from core to cladding, so it is known as step index. So this is, there is a step variation in the refractive index when we move from core to cladding or cladding to core. This is known as step index. So in step index fiber, the refractive index of core is uniform. If you observe carefully, the refractive index of the core is same, and the cladding is also made up of uniform refractive index. Core refractive index is N1 and cladding refractive index is N2. Both they are made up of uniform refractive indices. And we observe that there is a abrupt change called a step change in the from core to cladding or cladding to core takes place. That's why it is known as step index fiber. So once again, so there is core is made up of uniform refractive index N1 and cladding is made up of uniform refractive index N2. So as we move from cladding to core, there is a step change from cladding to core that we can observe from the diagram. That's why it is called as step index fiber. Next, second one, we get into the graded index fiber. See, in the graded index fiber, once again this is the core and the cladding of the fiber. When you come to the refractive index, the right hand side, if you observe, so this is the fiber axis. This is very important here. So with respect to the fiber axis, we can observe from the tip here, as you here the core is not made up of uniform refractive index. Try to understand, this is the important part in the graded index. That is, the refractive index is maximum at the axis of the fiber. I am talking at the center, at the axis of the fiber, and as you move away towards the core cladding interface here, as you move away towards the core cladding interface, it goes on decreasing. The refractive index goes on decreasing and till it reaches the core cladding interface. So this is the beauty of the graded index. And the cladding here, the cladding is made up of uniform refractive index N2. It is not going to change here. It is made up of N2, while the refractive index of the core, it changes continuously as you move away from the axis of the fiber towards the core cladding interface. So this we can explain once again. At the axis, from the axis of the fiber, as you move towards the core cladding interface, the refractive index goes on decreasing, but the cladding is made up of uniform refractive index. So this is something regarding the graded index. That's why you can say that in a graded index fiber, the refractive index of the core varies gradually as a function of radial distance from the fiber center. From the axis of the fiber, it goes on decreasing till towards the core cladding interface, and cladding is made up of uniform refractive index. This is regarding the graded index. Now based on this, the mode concept and the refractive index profile, now the optical fibers are broadly classified into 3 categories. So one by one we will see in our next slide. The first one is single mode step index fiber. So in the single mode step index fiber, so this the explanation is carried out through the ray diagram. Now this is the cross sectional view of the single mode fiber. It is observed that at the center the core will be there, and the core is of very thin, it is very narrow, of the order of 6 to 15 micrometer. Very narrow. It may change from text to text. Okay. So usually it is of the order of 6 to 15 micrometer, while the cladding, you can say it on the other side, cladding is of the order of 50 to 70 micrometer. The next one is ray propagation, how a ray is going to propagate inside the fiber, and we have discussed in the previous case, only one mode is going to propagate inside the fiber, therefore it is single mode. And based on the refractive index, it is easy to know that it is going to be a step index. This is a step change in the refractive index, therefore it is a step index, therefore it is called as single mode step index fiber. It means only one mode, single mode, and there is a step change. That is nothing but single mode step index fiber. This is the first type of the fiber. And important thing to know is that when some signal is with this some amplitude is transmitted through such fiber, a single mode step index fiber, at the output, this is the output what we are getting compared to the input and output. So output a little bit diminished amplitude we are going to observe. Okay. So as far as the input, the output little bit diminished amplitude is there, and little bit pulse broadening also we can observe here. This is the height. So this is regarding the transmission of a ray inside the single mode step index fiber. So the name itself indicates it is a single mode, only one ray of path, and based on the refractive index profile it is a step index, therefore we call it as single mode step index fiber. Now coming to this one, the core is very narrow, of the order of 6 to 15 micrometer, so that only the fundamental mode can be transmitted. Whatever the wavelength is there, no, what we are transmitting, only the basic, the fundamental mode, it can be transmitted through that fiber, only one mode. And as it is narrow, the core is narrow, so a special type of the laser it is required to launch the light. So that is nothing but the laser diode. So its wavelength is 1350 nanometer or 1550 nanometer. Usually this 1350 or 1550 nanometer, it is in the IR range, infrared range. It falls in the IR range. So this is the communication window. This is the 1550 right now, 1350 or the 1550 nanometer. It is the wavelength through which the light is transmitted through the optical fiber for the communication purpose. And moreover, this fiber is basically suitable for the long distance communication. So across the globe, the optical fiber what we are using is, majority of the fiber which we are using is the single mode step index for the communication. So this is regarding the single mode step index fiber. Second one, multimode step index fiber. Instead of single mode, now it becomes the multimode step index fiber. Now we'll try to see, based on the diagram we'll try to explain. So once again, this is the core diameter, so which varies from 50 to 200 micrometer, so which is very large compared to the wavelength of the light which is transmitted. Similarly, the cladding diameter is of the order of 100 to 250 micrometer. The core 50 to 200 and cladding is 100 to 250 micrometer. It is very large compared to the single mode. And coming to the ray propagation, we observe there are more number of the ray of paths that can be transmitted. Therefore, it is multi-mode. More than one path exists. And coming to the refractive index profile, we observe that it is going to be the step change, that is the step index. Therefore, this is known as multi-mode step index fiber. Now, based on the signal, when the input signal is fed through the fiber of certain amplitude, we observe that there is the decrease in the amplitude. The amplitude has decreased and the pulse broadening has taken place. So whenever such area of light is transmitted through the fiber, the pulse broadening takes place. So over a certain distance, the amplitude decreases, means strength of the signal is somewhat decreased and pulse broadening takes place. So due to this, it is not desirable for the long distance communication. Previously, single mode, it is desirable for the long distance communication, while this multi-mode step index fiber, it is not designed for the long distance communication. Now here once again we will brief it. The core of the fiber is very large, so that it supports many number of modes to transmit. And the sources what we are using to launch the light, even the ordinary the laser light which is available in the lab, even we can launch the light into the multimode fiber. Even we can use the LED, the light emitting diode. LEDs also can be used to launch the light inside the fiber. Easy to launch because the core diameter is very large. Easily light can be launched into the fiber. As I said, it is not desirable for the long distance communication. So So for a very small campus or the area, we can call it as the LAN, local area network, the LAN. For the LAN purpose, we can use this, the multimode step index fiber. Usually the small, the campus, the industrial area, so very small region we can use this as far as communication is concerned. The third type is nothing but the multimode graded index fiber. This is the third type of the fiber, that is nothing but the multimode graded index fiber. Usually it is known as GRIN, 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 graded index fiber. Once again, based on this, the particular the diagram, we would like to explain. Here the core diameter is same as case of the multimode fiber previously we discussed. No, the fiber diameter remains same, that is core is 50 to 200 micrometer and the cladding is 100 to 250 micrometer. And coming to the ray propagation, here a ray of light is going to take the helical path, so some curved path is going to take place. Clearly you can observe from the diagram. Okay, such a curved path is going to take place. Such a curved path, a ray of light is going to trace the path. Then here also more than one mode exists, therefore it is going to be multi-mode. And coming to the refractive index profile, it is observed that it is a graded index. It means the refractive index is maximum at the fiber axis, and as you move away from fiber axis to the core cladding interface, it decreases. Therefore, on the basis of the refractive index profile, it is graded index, and it supports more than one mode, therefore it is multi-mode. Therefore, this is going to be, we call it as multi-mode graded index fiber. And coming to the area of light, when it is launched with certain the input signal, we do observe this is small, there is a change in the output signal, but compared to the multimode step index fiber, here amplitude is not that much decreased. So even these can be these are suitable for the long distance communication also, but it does have some disadvantages. Therefore even this is used for the short distance communication. Now core is, once again the core is very large here, so that it supports more number of modes. And once again the laser and the LED sources can be launched into the fiber due to its dimension of the fiber, and even it is also used for the communication. So altogether there are the three types of the optical fibers. First one is single mode step index fiber, only one mode exists. Next one is multi-mode step index fiber, and the third one is multi-mode graded index fiber.